Found in the outskirts of New York, known for its wildlife and nature, our beautiful college town of Ithaca has a majestic scenery that truly makes it gorgeous. Yes, I said gorges. Gorges are one of the bodies of water that Ithaca is known for. If you don't know exactly what a gorge is, it's a narrow valley between hills or mountains, typically with steep, rocky walls and a stream running through it. Now you may be asking yourself, what does this have to do with fluid mechanics? Well, the very thing that makes the flow of water in a gorge possible and makes it as beautiful as it truly is in fact hydraulic jump. Hydraulic jump makes Ithaca gorgeous. We are Group 5 and we're about to tell you why. Special thanks to Professor Sunny and PhD student Anupam Pandey for your assistance. Hope you don't fall asleep during our video. Hydraulic jump is a natural phenomena that occurs whenever flow changes from supercritical to subcritical flow. Supercritical flow, labeled as U in our derivation, is a flow whose velocity is larger than the wave velocity. In this transition, the water surface rises abruptly, surface rollers are formed, intense mixing occurs, air is entrained, and often a large amount of energy is dissipated. We are interested in the ratio of heights from the taller section, section A', B', to the smaller section, section AB. To derive this ratio, we use the conservation of momentum equation in the x direction. We end up with a momentum flux term and a surface pressure integral. We use the dot product of n and v to find the momentum term along both AB and A', B'. We do the same with the surface pressure term. Next, we relate the velocities to the heights using the conservation of mass equation. We solve for u and plug this into the conservation of momentum equation we already derived. Now we have an equation for u prime in terms of h, h prime, and g. We can plug this equation back into that same conservation of momentum equation we derived. This gives us a quadratic equation. Using the positive root of the quadratic formula and some simple algebra, we then find the ratio of the heights. We did the derivation because we didn't want to hydraulic jump to conclusions. Experimentally, we sought to replicate the hydraulic jump phenomena by varying water jet flow rate as it hit a flat plane. We can see that as the flow rate increases, the radius at which the fluid transitions from supercritical flow to subcritical flow increases as well, seen visually as the hydraulic jump. This makes sense because by conservation of mass, velocity must decrease with radius. Thus, increasing jet flow rate increases the radius at which the velocity transitions from supercritical to subcritical flow. We also used a few methods to better visualize water movement in the supercritical region. Dye allowed us to visualize conservation of mass and the effect that movement away from the jet has on the velocity in the supercritical region. Adding beats to the water let us think about how a dog swimming in the gorge, similar to the one you saw in the video, might interact with a hydraulic jump. Try not to overflow with excitement. Hope you enjoyed our video! Sorry if these puns put a damper on your day.